Okay, so we move on to study lecture 2. So in lecture 1, we basically have a study, okay, the nature of IoT and also the definition of IoT. In particular, in lecture 1, we know that the 3 pillars underneath IoT are controller, sensor, actuator. Then on top of these 3 pillars, we have software. And the software, you can create a lot of layers of software. All right. Now we want to know what should be the basic skill knowledge for us to build up IoT. So the starting point is to know how to interconnect, okay, different things together to build up a network. All right. Then at the basic level, what should be the technology or methodology for us to build up a network? The answer is either to use a synchronous communication methodology or asynchronous communication methodology, right? So today, all the microcontrollers support the implementation of these 2 methodology, all right? So today, now we are going to spend 2 lectures to study synchronous communication and asynchronous communication, and also to know how these 2 communication methodology have been implemented by ARM microcontroller. All right. So you will see lecture 2 will cover the working principle of undertaking synchronous communication. And this principle is an international standard. All right. So you should not ask this question, why doing synchronous communication in this way? All right. Because this is an international convention or standard. All right. So we just understand, all right, how to undertake synchronous communication. Then follow this way of doing synchronous communication. The good news to you is this has been implemented by microcontroller. Then you just need to know how to operate microcontroller, okay, in order to achieve synchronous communication. This is very much similar to the case that you want to be a driver of a vehicle, all right? Then in the whole world, we have 2 traffic rules, because the driver could be on the left-hand side of the vehicle or the right-hand side of the vehicle, okay? So in Singapore, for example, the driver is on the right-hand side. In China, the driver is on the left-hand side. You should not ask this question, how come, okay, the driver is the left-hand side, right-hand side? You should not ask this. You just follow, okay? If it's the driving rule is the driver in the right-hand side, then you want to know what should be the rule. Then you follow the rule, that's it, all right? So for example, you purchase a car which support you to drive on the left-hand side or right-hand side. Then you just know how to use this car, all right? You should not worry about the, okay, how to get the car which allow me to drive on the left-hand side, right-hand side, all right? So you should not worry, okay? The good news is you just know the rule, and you purchase the hardware which implement this rule. That's it, all right? It's like when you purchase a car, you should never ask a question, how come this car has been designed in this way, all right? So your job is as a driver, just look at the manual, a user's manual, to know how to use the vehicle. Then here you must have the same mindset. Put yourself into the mindset of a user. Don't put yourself as a mindset of a student or inventor or designer. Put yourself into the mindset of a user. I'm a user. I follow the rule. Okay, I follow the rule imposed by the designer of the hardware. It's like when you want to become a driver. Okay, You just know how to use the car. You should never ask a question, how come this car is designed in this way? Okay, you should not put yourself into the mindset of a designer, all right? Otherwise, you will never be able to follow, okay? But, okay, adopt this mindset of a user. But difficulty is due to the complexity with the microcontroller. The hardware, also the hardware is very cheap, but it is much, much more complex than the vehicle itself. To drive a car is easier. Basically, you control two parameters, steering and the velocity. But to use a microcontroller, you need to configure a lot of sensors, all right? That is why you need to know, okay, your intention and a little bit how to configure the hardware, because hardware will help you to do things. You just tell hardware your intention, okay? Your intention of doing synchronous communication. That's it. Keep this mindset of a user, then you will easier to follow this lecture, okay? Don't put yourself as a student learning theory, all right? Or learning mathematics or other working principle, etc. All right? So now put yourself into the mindset of a user, all right? So first, I will tell you what is the basic of a synchronous communication, then how to do the input. So when we talk about the communication, always keep this in mind. So we must have a two-party which exchange information, all right? So you must think of a two device, input device, output device, all right? So this also is another very important background knowledge, is when you drive your vehicle, you must think about the road, think about your vehicle, all right? So you should not say, I only have a vehicle, I don't care about the road environment. Then you will have a lot of accidents, all right? So when you drive your car, think about the vehicle and the road. When you talk about the communication, think about the two unit of device exchange information, all right? So this is why you have an input device. But actually, each unit could undertake input, output, so then they can exchange information in both directions. Then lastly, the good news to you is you do not need to know how to implement this methodology or international convention for synchronous communication, because all these things has been implemented by hardware. It's like when you want to drive your car from Beijing to Shanghai, you should not worry about how to implement a vehicle so that you are able to drive from Shanghai to Beijing. All right, you should not worry about. You just need to know how to use the car offered to you in order to drive from Beijing to Shanghai. All right, so it's the same. How to use this hardware offered to you by company, by the market, so that you can implement this synchronous communication. That's it. Keep the user mindset in mind, then you will enjoy the study of this lecture. Otherwise, it will be painful. You will get lost. All right. And it's like when you become a driver of a vehicle, you remember, I do not know any one of you has a driving license or not. You need to remember a lot of terminology. That is another task for a user to undertake. Memorize terminology. All right. Don't ask a question, why? Why is this name? It's like when you drive a car, you have a speed ratio, like gear ratio. Okay, gear ratio 1, 2, 3, forward, inverse. All right, and you have a headlight, and you have a lighting to indicate turn left, turn right, etc. All right. So all this terminology you need to memorize so that you will be familiar with this. All right. So good news is this lecture will expose you to some terminology related to microcontroller. Then will help you to study microprocessor system in future when you take up the courses. All right. So this is a benefit to you. Okay. Within 1 hour or 2 hours. Okay, you will expose to the major technology related to microcontroller. All right. Okay. basic of a synchronous communication. Why do we need to communication? You remember Internet of Things means what? It's a massive network of a sensor actuator. We need to implement the information flow or data flow inside the network. If there's no information flow, data flow inside the network, then we should not call it a network. Then what's the point for us to build up a network? All right, network means what? Inside there must be data flow and information flow. And the representation of a data at the lowest level is a binary number. Binary number means what? 0, 1. All right. So keep this in mind. All right. So at the lowest level, you have a single bit, but the basic unit of a measurement for data is not a bit, it's a byte. That means you put the A bit together, form a 1 byte. 1 byte has an A bit. Okay, each bit take a value 0, 1. Then you can do a simple mathematics. I guess this you can handle it quite easily. With the A bit, each bit take a value 0, 1. How many combinations are there? So actually answer is what? 2 raised to the power A. So it's 250. You just do a simple calculation. Number 2 raised to the power A. So equal to 256. All right. So if 2 raised to the power 16, 32, then what should be the value? You use your calculator. All right. So these are simple mathematics. Okay, quite easier. All right. So keep this in mind. We need to exchange data. Okay, and achieve this data flow inside the network. Then how to do it? So first technique is called synchronous communication. All right. So why do we need to have a synchronized? Synchronous means a synchronized. Why do we need to have a synchronized communication? Now this example help you to understand. All right.
If graphic, high speed, high accuracy, synchronized motion.
You see, there's no collision, you know.
Linear servo axes.
So without synchronization, then you will collide, all right?
A rotary servo axis.
So the low speed is easier, but high speed, now you see, at such high speed, we can still achieve synchronization.
With a Q172H motion controller and 6 servo amplifiers, all MRJ3B amplifiers with inbuilt SSCnet3 communications capability. SSCnet3 is a fiber optic network unique to Mitsubishi Electric. It provides high-speed communications between the servo amplifiers and the motion-controlled CPU, with data transfer rates of up to 50 megabits per second. The amplifiers used on the servo demo rig are normal MRJ3B models, which are more than equal to the task of running in integrated automation systems where there are complex synchronized multi-axis movement sequences. 3 of the amplifiers drive the linear servo axes, which are inline mounted Mitsubishi Electric LM series motors. The remaining 3 amplifiers drive Mitsubishi Electric HF-KP rotary axes from the MRJ3 servo series. High-resolution, absolute position encoders on the rotary axis offer 262,144 pulses per revolution output. This allows for extremely accurate control over position, torque, and speed. Operator control and monitoring is provided by a Mitsubishi Electric GOT15 HMI linked to the PLC through the bus on the back plane. It allows high-speed data transfer from the servo amplifiers to the HMI. The design of the MRJ3 series provides easy installation and configuration, regardless of the application. The control parameters are set automatically by the real-time auto-tuning system developed by Mitsubishi Electric. This function continually adjusts and optimizes the control parameters for the current operating conditions.
Okay, so this video should be good enough to convince you about the importance of doing synchronized data communication in order to achieve a synchronized action. Because without the synchronized data communication, how you achieve a synchronized action is not possible, all right? So it's very, very important, all right? Then for exchange information, just now I ask you, always think about the two party. You have a device A, device B, then exchange the data, all right? So you may have a scenario of having two party which are located inside the same system, all right? So it's inside this PCB, printed circuit board, you have a MCU, you have a FPGA. So these two device exchange the data. Then in this case, we call it an intra-communication, all right? Then we may also have a two system. They want to communicate between them. Then in this case, we use the term intercommunication, all right? So this is a typical scenario, all right? So for intra-communication, we will do synchronous communication. For intercommunication, due to the long distance, in order to reduce cost, we will do asynchronous communication. Asynchronous communication is still synchronized communication, but it is synchronized by software. Synchronous communication means it's a synchronized communication, synchronized by hardware. Okay, so for example, we to see bus. For those of you, if you study industrial automation, you may heard of this terminology, all right? So it's widely used in industry. Because here you see this serial clock. So serial clock means is a dedicated signal for synchronization, all right? So then in this case, we are doing, this is the implementation of synchronous communication protocol or methodology, all right? Just think in this way. And then just now I ask you, when we have a two device, like here, you have a master device, you have a lot of slave device channel, right? But each time, only two of them can exchange the data. It's not all of them, because at the time window, only two involved, right? Then another time window, another two, right? So keep this in mind. So this is a communication always occur in time. So you have a time window, right? So within the time window, okay, we communicate what? We communicate the data. And now this slide help you to understand what I'm talking about, all right? The basic unit of the data is a byte. But inside the byte, we have a bit, okay? By one byte is what? A bit, all right? So therefore, at the lowest level, we communicate a string of a bit, but only at the one level higher, we understand we are doing communication of a series of a byte, all right? This is why you need to indicate what is the starting byte, what is the ending of a byte. Then we communicate byte by byte. Also at the hardware level, we understand we are doing communication bit by bit, all right? So keep in mind, conceptually, we only talk about the byte because the basic unit of a measurement of a data is a byte, conceptually. But in terms of the hardware, okay, the basic unit of data is a bit, right? So you see there's a gap, all right? Conceptually, we think in terms of a byte, but hardware can only communicate in terms of a bit. Hardware only communicate in terms of a bit. Then there's an issue for us to tell, okay, the hardware, especially when you receive something. What is the starting bit for one byte? What is the ending bit for one byte? What is the starting bit for another byte? What is the ending bit for another byte? All right. Another concept is when you communicate the data, the communication occur within the time window. All right. So you see, this is a time window from T1 to T2. We communicate how many bytes? In this case is what? 3 bytes. 3 bytes is conceptually. Then for hardware, let me need to talk about how many bits, all right? Because we have extra byte for acknowledgement to indicate the end of a previous byte, the start of the next byte. All right. So this is some extra knowledge for you to know. All right. Another knowledge for you to know is synchronized communication. So you will see you have a data signal, you have a clock signal. So we use a clock to achieve a synchronization. Just now you see the motor turning at the high speed. How come they can synchronize perfectly without the collision? If you think in terms of analog system, it's impossible to achieve that scenario, right? But if you think in terms of a digital system, everything is under the control of the clock. If they share the same clock, then it's easier for you to understand, because for one clock, they're doing one thing, another clock pulse, they do another thing. Okay, so everything is under control of the clock. Clock is what? It's just a square wave formula, right? Then another terminology for you to know in digital computer is for each pulse, we have a definition terminology, rising age. When there's a transition from 0 to 1, is a rising. We have a level low. If it's 0, we call level low. If it's 1, we say it's a level high. These are the terminology you must memorize, all right? You should not ask why, okay? There's no why, it's just give it a name. It's like you call your friend, your classmate is Zhang San, Li Si. But this name is given by his parent. You should not ask your friend why, how come your name is Zhang San? Okay, you should not ask this question. Why your name is Zhang San? Okay, don't ask this. Okay, just memorize. Okay, your friend is called Zhang San, another friend is Li Si. Finish. All right. So here is the same. Low, level low, level high, rising age when there's a transition from 0 to 1, and falling age. Okay, we will come back to this term when there's a transition from high to low. That's it. Very simple. Okay, so for those of you, if you are new to microcontroller, maybe the difficulty is to memorize all these names. It's the same the first day when you join a university. If let's say your class has 40 students, the first task for you to do is what? Memorize 39 students' names inside your class. Yes or no? All right. So you must do the same once you join university, day 1. And if your class has 40 students, then you must remember 39 students' names. Okay. Then you will never ask this question. How come your name is like this? How come your name is like that? All right. Okay, Sam, if this is the first time for you to know what is a microcontroller, then you must remember this terminology, all right? But this is good news to you, you remember. Then in future, when you study microcontroller, you feel comfortable, all right? Okay, so then we need to, since we need to synchronize data communication, okay, by using the clock, all right? And at that conceptual level, we need to know what is the timing for the sender. You see these two technical terms, another technical term, to transmit, to receive. To transmit means is a sender. To receive is a receiver. So you have a transmitter, you have a receiver. Transmitter is to send, to write. Receiver is to read, to receive. These are the terminology used in digital computer. Now you see how to do read, how to do write. Okay, convention is no, there are different convention. You can either use a rising age or falling age to synchronize the write operation. Write means send out the data into the physical line. All right. So here I just showing you example of when there's a falling age, clock will fall from a high to low, then which will trigger write operation, write the data into the physical line. Then we wait for the data to stabilize on the physical line. Then when there is a rising age, the clock will make a transition from low to high. Then it will trigger read operation. then the receiver will start to read. You keep this dynamic activity in your brain, then you will see write, read, everything is synchronized, all right? And this corresponds to 1 bit. So in one cycle, we just communicate 1 bit. So it's a bit by bit communication, all right? But at the lowest level, the hardware do not know whether this bit is a starting bit of 1 byte or ending bit of another byte or not, all right? Because hardware just, okay, I just blindly send out all the bit. So this is why you must keep this synchronization in mind. Synchronize what is not to synchronize the bit, is to synchronize the byte. Remember, the basic unit of a measurement at the conceptual level is byte, but the basic unit of data at the hardware level is a bit. Okay, keep this in mind. Then conceptually, everything must synchronize. You may say, this byte belong to this device, this byte belong to another device channel, all right? But hardware does not know. So you need to add in extra information so that the hardware will, okay, will interpret the synchronization correctly, synchronization of a byte correctly. So keep this vision in mind, or this concept. Synchronization of a bit at the hardware level is always synchronized. Now we talk about the synchronization of a byte. Now we need to add in, do something extra. All right, okay? So then, so this is the concept. But one strategy is if you have a hardware clock signal for you to play with the synchronization, a simple way for you to achieve synchronization is what? So every time I just blindly transmit A bit, right? A bit one session, then another A bit, another session, all right? By hardware. So this is we call it synchronous since support of the hardware, okay? Then asynchronous communication with the support of software only, okay? So asynchronous communication does not have hardware support for synchronization, all right? So just keep this scenario in mind. That's it, so it will be good enough, all right? Then another concept is just now I mentioned, when you exchange of data, okay, for the same data, from a data point of view, we have a concept of a sender, transmitter. Who is a transmitter? Who is a receiver? Okay, from data point of view, all right? Then from a device point of view, a device could play the role of a sender or transmitter or receiver. It's like a robot. A robot could send out the data at the same time receive the data. Keep this in mind. That means for a unit inside the node of IoT, this node could be transmitter, could be receiver, all right? Then from the data point of view for a single byte, then we can talk about who is the transmitter, who is the receiver, okay? Keep this in mind. Then this is why we talk about the direction, input, output direction. And here is a scenario, you see? And this is the master, you see. SPI is a terminology, is a serial peripheral interface. S means a serial, P means peripheral. Peripheral equipment of your CPU. I means interface. Then in this case, this is a master device. This is a slave device. All right. So you see, master output MO is another terminology in digital computer. Master output, slave input. Okay, because this data from a data point of view is output from master. Then input this data will enter the slave channel. Then slave input. So from data point of view, okay, this data output from master. Then it will become an input to a slave. That's it. All right. Then you see here is in parallel slave output, because from data point of view, this data output from a slave enter into the master. That's it. All right. So these are the terminology. Once you know all these basic terminology, then the principle is very simple. How to do the serial input. The input means it could be, okay, from data point of view, input to a device is very simple. But from a device point of view, this device could be input device, output device, okay? So for example, input to master, you see MI is here, or input to slave, SI. So input, we can talk about that, master input, slave input, all right? Okay, this slide also help you to understand how to use a microcontroller. It's like how you drive your car. Once you sit enter the car, you may do some adjustment. This adjustment of your body, the height, your vision, whatever, right? This adjustment is called as a configuration. So you just need to know how to use a register to do the configuration. Register is like a switch. Okay, you switch on, switch off this sensor. Then you tell the hardware what is your intention, all right? And how to physically communicate out the bit by bit. So the good news is we use a shift register. Shift register basically is an output device in a digital computer, all right? So on top of that, we have a data register is to hold the data to be received or to be transmitted. Then we have a control register is to configure, all right? The microcontroller, they will tell the microcontroller your intention. Status register is to, for the hardware report to you, okay, what is the current situation inside the hardware, all right? So if you just know these three type of register should be good enough, 4 type, okay? Status register for you to know the condition of a microcontroller. Control register is for you to configure your microcontroller. Data register is a buffer, okay? You send for you to retrieve the data or to store the data, all right? Shift register is like an actuator. You take action, okay? You transmit out, ship out the bit by bit, all right? So something like that, okay? Then here illustrate, okay? So it's an example. You look at the time axis, okay? So in this case, so you see the clock signal when there's a foreign age for input operation, because we talk about the input. Then you see when there's a rising age, we do the read. Input means what? Is to read. Output is write, right? So the master in, he will read, and the slave will output. When there's a foreign age, slave will output. Then when there's a rising age is here, the master will read. So you see, when there's a rising age, we will read 1 bit, 1 bit, 1 bit, all right? And how to synchronize? We just open a time window for 8-bit or 9-bit, all right? Then eventually you just transmit out the 1 byte. So it's a byte by byte. So you see, the hardware will provide this time window, only allow 1 byte to send out, all right? So this is a situation. Then how about output? Then in this case, output is the same, is a symmetric, all right? Once you have an input, you have an output. Then the output is to send out the bit by bit, all right, to the data line. Okay, it's the same. So you need to configure both sides, right, so that they will run in at the same clock, right? Then in this case, slave is output. Then when there's a foreign age, then the data will slave output is will write into the physical line, right? Wait for the master to do the input. You see, slave will output at this time, then master will read in at this time. Okay, so keep in mind. Okay, write, read, write, read. All right. So this, so everything is under the control by the clock. So if everything is under control by the exact timing, now you understand. Even you run at the high speed, it's easier to synchronize. Quite straightforward. All right. Okay. That's about the principle of synchronous communication. Now you may want to know, okay, how to use or make use of such principle. The good news to you is all the microcontroller provide you the hardware support for you to achieve a synchronous communication. Then you need to choose, okay, the right microcontroller. Okay, today Cortex is very popular, and the Cortex give you this support. Now you see this SSI is a synchronous serial interface. All right, synchronous serial interface, SSI. So Cortex microcontroller provide the hardware support for synchronous serial communication. So all the microcontroller provide this, all right? So all the microcontroller, otherwise they should not be sold as a microcontroller. Okay, that is good news. Then you must put yourself as a user. It's like when you want to drive a car, put yourself as a user of a car. All right. Now put yourself as a user of a microcontroller. Okay. So why you want to drive your car? Because you want to enjoy driving, or you drive your car to go to school, go to your workplace. All right. Then why do we use a microcontroller? Basically, we want to use microcontroller to do control automation. And in the context of IoT, we want to use a microcontroller to achieve communication, to build up a network, right? So you see, we can use a microcontroller to build up a network. And then we have a IoT. Very simple, right? Okay. Then just now I ask you, okay, you must put yourself as a user. What is your role if you use a microcontroller? Your role is what? User. You are not the designer of a microcontroller. All right. So then in this case, you must know your problem. You must know your solution. Then you just implement your solution on the IoT, on the microcontroller. For example, your problem is what? To use a microcontroller to build up a network in your IoT. That is your problem, China. All right. Then your algorithm is okay. You want to communicate byte by byte, all right? Then what is the content of the byte? You up to you to define, okay? Because at a higher level, you can use the byte to synchronize communication of a meaningful data, all right? So it's up to you. Here, that means you are totally free to design your own algorithm solution, all right? Okay, then what to know? Actually, you need to know, okay, what is microcontroller, etc. But today, you just put yourself into a user. I just show you the example, okay, expose you to the, okay, to the how to use, okay, the way, expose you to the way of how to use our microcontroller in order to achieve a synchronous communication. Okay, so you just know that this thing happens, but if you want to really know more detail, then you need to study microcontroller course. All right, okay. So, but good news is actually it's very simple to use microcontroller. Okay, because you just need to know the meaning of all these register. Okay, then you know how to write the value into the register. Then in terms of a programming skill, you just need to use one of these three instructions to write the value into the register. All right. So basically, you want to know the meaning of each bit inside the register, then determine what should be the value to write into the register. Then how to write the value into the register? You just use one of these three instructions. Then what is register? Register, just for you, is to consider. Just now, I already asked you to just imagine a register is like a hotel, okay? But for ARM microcontroller, okay, the hotel room is different. This hotel room, each room can house 4 bytes. Now, because this is a 32-bit microcontroller, 32-bit microcontroller means what? It's a hotel with a room, so that each room could house 4 bytes. Why 4 bytes? Because 4 bytes has a 32-bit. So this is why we call it 32-bit microcontroller. That's it. So I have a one room. Each room can hold has a hotel room now, a lot of room, many room there. Each room can only house 4 bytes. Okay, each room must house 4 bytes. If let's say you do not have so many data to fill up the 4 bytes, but it's okay because one room is there. It's like you cannot have a room, have a hotel, have a room, and dynamically you change the size. It's not. It's a fix. once you construct a hotel, the size of a hotel room is fixed, all right? For microcontroller, it's the same. Register is a fixed size. Okay, every register for 4 bytes. Either you use it or use part of it. That's not matter, all right? Okay, so then for this ARM microcontroller, why I just now tell you this is a very good microcontroller with the highest performance cost ratio, because this CPU is very cheap, but they give you a lot of flexibility. It's high performance. Here you see this, you just pay attention to this number, 4 SSI module. So it means the single device with one ARM microcontroller, you can communicate with 4 other devices. Then you can imagine you can build up a network, okay, in 4 directions. Then you have a matrix of a network of IoT. Yes or no? That means a 2-dimensional network, right? With a matrix of node, right? But each node can interconnect with 4 adjacent nodes, right? So this 4 is very important for you to know on the context of IoT. Like I said, then you have a buffer, blah, blah, blah. Then you see this name of a big company. Freescale is a US company. Microwire is a US company. TI, Texas Instruments, is a US company. So they have their own protocol, own convention for synchronous serial communication. So then the ARM Cortex microcontroller implement the industrial convention for synchronous communication from Freescale company, Microwire company, Texas Instrument company. That's it. And actually, you can also implement your own company, ABC company, up to you. All right. So from here, it's very easier for you to see the power of a microcontroller. Actually, with the microcontroller, you can have your own invention. All right. And here it just remind you 1 byte is equal to 8 bit. Okay. So this is basic knowledge. Then what is a microcontroller? It's just this single chip. This chip have a 64 pin. Okay, this 64 pin allow you to interface with other devices, hardware. All right, you can do the soldering connection. So then you need to memorize all this meaning of this pin. All right, slowly you will get used to it. All right, by now, for example, there is a pin for transmission, reception, clock signal. This is for synchronization. This is for synchronization at the bit level. This is for the synchronization at the byte level. All right, byte. Now you remember at the hardware level, the bit is always synchronized. Conceptually, we need to synchronize the byte. Then we have a hardware support to synchronize the byte. Why? We have this signal. Friend, is for 1 byte. All right. So we have a signal for bit, synchronization for bit, synchronization for byte. Done already. All are supported by hardware. Okay, that's it. All right. So then how to do the connection? You see, this is the pin inside the chip. And then this is the name, okay, of the pin for serial communication. Then you will see this is 000. This is for one IO, okay, for synchronous communication. Then you see this is 1111, 2222, 3333. This help you to understand this number 4, because we have a 4 unit of IO, right? Something like that. Get it? Now you understand why this is 4. It's 000, 111, 222, 333. If you want to physically do the connection, then you just find out what are the pin number on this chip. This is a chip integrated circuit chip channel. Then you find all this number here, 1, 2, 3, 4, all the way to 64 are here, right? Then if you know how to read this number, is good enough. Then in microcontroller, there's another concept you just memorize. We call it a port. Port A, P means a port. It's like the door, right? You have a door 1, door 2, door 3. Port A. Port A, each port actually is 1 byte. So each port is physically correspond to a physical pin. You see, because this port pin 2 of a port A correspond to this pin. So it's the output port or input output port. Okay, but the port correspond to 1 byte because we will have an address to refer to it. All right. So just now I mentioned, okay, in the hotel, actually 1 byte has a 1 room number, but for Cortex, you can imagine is a super room. Super room, you have a 4 individual room. Each individual room has a address. So you can say this is a room 1.1, 1.2, 1.3, 1.4. Just imagine like this. Because inside the room, you have a 4 byte, but each byte also has a door, has a key. You just imagine like this. It's a super room, has a 4 smaller room inside. Each room has a key, all right, individual key or individual. The key, just imagine as an address, all right, something like that. Okay, so you have a port D, port F, etc. That just help you to know that the input, output, the pin, we can group them together. Okay, A pin group them together to form a equivalent 1 byte hardware implementation of 1 byte. Okay, something like that. Okay, so but only complication little bit like, okay, how to specify the frequency of the clock. Okay, so as a student, you may say, I just give a number of frequency of 100 Hertz and 200 Hertz. The life is easier. All right. So your suggestion is good. So, but for the designer of the hardware, they are not doing that way. Okay. So they do the calculation in this way, complicated. All right. So system clock frequency divided by prescale divider, then divided by 1 plus this number, all right? So then once you choose a clock, you choose this one, you need to know what should be this one, what should be this one, okay? But there's a formula for you to calculate, you should not worry. Let's say system clock is 20 megahertz. There's a prescale divider, we choose to be 2. The SCR, we choose it to be 9. Then what is the bit rate of this one? You just do this calculation and you get this number, all right? So this is intentionally by the designer, all right? Then you should not ask question of why, okay? Okay, Ken, okay. So this is a slightly complicated with the use of a Cortex, okay? But anyway, it's like what I say, you follow this law, okay? Just do this, it's not a big deal, okay? Then for TI's convention, you just pay attention to, okay, you see, to write, now he use, it's not, when there's a foreign age, you see, this is for synchronization of a bit. So when there's a rising age, he do the write operation, okay? And when there is a foreign age, he will do the read. So this is for read, this is for write. This is only thing for you to know. Then this is to synchronize 1 byte, byte by byte, okay? So foreign age will indicate the start of the 1 byte. Then another convention, okay, this is just for you to know, most significant bit, least significant bit. So this is bit 7 of a 1 byte. This is a bit 0 of a 1 byte, all right? In case of a 1 byte, a bit, all right? So it's a bit 7 all the way to bit 0. That means first send out the bit 7, last one will be bit 0, okay? These are the terminology, just memorize, okay? If let's say you want to continuously send out the a series of a byte, you see, this is a 1 byte, John, 1 byte followed by another byte. So you see, this is to synchronize byte by byte. This is to synchronize bit by bit, okay? So this is the TI's convention. Then for microwires convention, then you will see, okay, is a rising age is for you to read, okay? Rising age is for you to read. So if let's say this is a receiver, you see, there's a rising age to read. So it's opposite to TI. So this is why you need to pay attention, all right? So then this is to synchronize. But this one can do bidirectional communication. That means when I read in one byte and the transmitter and at the same time can send out the one byte. Okay, so it's a bidirectional communication. All right. Then this is a okay for the continuous transfer. Then transmit, that means continuously send out the series of a byte. Then receiver continuously receive a series of a byte. All right. So this is a microwise protocol, but Freescale is slightly complicated. It totally changed the rising age and falling age. He used a new name called first age, second age, right? Then he give an extra 2 bit to indicate whether it's a first age or second age. Then he do the synchronization. Here I just showing you, if you set these 2 bit to be 00, then this will be the first age. First age will trigger to read. If you are the receiver, to read. If you are the transmitter, I transmit out the data for the receiver to be read. Okay, the data is to be read by the receiver. If I am the device, I read. Okay, so when the first age rise, if I'm the receiver, I read. If I am a transmitter, then I wait the data to be read by the receiver. Okay, this meaning. Okay, and if you use 10, then this signal could be first age. Okay, when the clock has a falling age, the falling age become first age. You see, when it's 00, then rising age is the first age. When it's 10, then the falling age is the first age, right? Etc. Then for second age is the same. If 11, rising age is second age to read, to be read. Then when it's 01, then the second age is a falling age of the clock signal. So this is slightly complicated, okay? So because this is an industrial convention, something like that. All right. So that's about the basic of Cortex M4 for the use of synchronous serial communication. Then how to operate it, I just quickly go through it. So basically you need to configure input, configure internal process, configure output, all right? And then you run it, that's it, all right? So I'm not going into the detail, otherwise you will get lost, all right? First, you must choose, tell what is a system clock, okay, the clock frequency. You can either choose a system clock or the clock frequency provided by the input output the system. Then for internal process, we need to configure, okay, what's the data size? By default is an 8 bit. You can, okay, have a data size of 16 bit or 5 bit, etc. All right. Then you see the clock rate. You see SCR is appear here. Okay, later I will show you there's a calculation. So you just store this, what is the SCR number? You just write here. Okay, now how to read this one? You just consider this is a one super room in a hotel. Inside this super room, you have a 4 smaller room. Each smaller room has is 1 byte, has 8 bit. So you add together is how much? 32 bit, John. Bit 0 all the way to bit 30. Each room, each super room has a key. The key is here. Because we have a 4 unit for synchronous communication, we need to have a 4 key. 4 key are here. So the address is a key. How to get the address is the base address plus offset. You get the absolute address. Address of a memory corresponds to the room, the key of the room of in the hotel. All right. Then for Cortex M4, you just consider is a hotel with many super room. Each super room has a 4 smaller room. Each smaller room house 1 byte. Finish. Understand? One super room has a 4 small room. All right. Then the super room has a 1 key. Each smaller room has also 1 key. All right. Okay. Key means what is address. Then the super rooms address are here. All right. Then you just the super rooms address plus 1, you get to the next smaller rooms key. All right. Then plus 2, then the second smaller rooms address plus No, +0 is the first small room's key. +1 is the second smaller room's key. +2, +3. Then you get all the key, okay, inside the super room. That's it, right? Okay, very simple. Okay. Then you see, turn on. How to power on? You just set the 1 bit there to turn on, and whether this device is master slave, you just decide. You see, now you understand. We have this unit. It could be master, it could be slave. Very simple, right? So you just tell, okay, this one is slave, this one is master. All right. So then for output is more or less symmetric, I guess. All right. So now you see, you can here you must set the this value, prescale. You just write here. Okay. This also exists for, this is shared for input-output operation. This is why in the previous slide, you see where to set this number, SCR. Here you see where to write this value. Here is right to here, all right? And you have 4 super room, okay? So because you have 4 such synchronous serial communication, so you have 4 super room for you to house this value, prescale divider, all right? Okay, and okay, here is repeat just now. For you to house this SCR, all right? You see, okay, and here you see presence of these 2 digits is for free scale. You remember free scale has a first age, second age, all right? So it's under control of these 2 bit. So you decide, all right? So then this is okay. There's another concept of interrupt. Interrupt basically is a signal. It's very simple because some students will feel, oh, this is a beginner interrupt. Actually, it means a signal. It's an internally generated signal. That's it. It's very easy for you to understand. Okay, how do you know that you are hungry? Your brain may know that you are hungry, John. Why your brain know you are hungry? Reason is what? Your stomach send a signal to your brain. And this signal in terminology of a computer is called the interrupt. That means your stomach send the interrupt to your brain so that your brain, if your brain pay attention to this signal, then your brain say, I'm hungry because my stomach is empty. If your brain do not pay attention, then even your stomach is empty, you may not feel hungry. Okay, it's the same situation. So hardware generate interrupt. CPU whether pay attention to it or not, okay, is another issue. So you will see we can set the mask. That means don't trouble the brain. Okay, also signal is there, but don't let the brain pay attention to this signal. So this is why we call the mask. Okay. Also, the hardware have a signal, but don't let the signal go to the CPU, go to the brain. It's like when your stomach is empty, but don't trouble your brain. It's like this, right? So, okay, understand? It's a very simple concept. So it's hardware generated interrupt. And then how to clear interrupt? You write the 1 here to clear the interrupt, okay? Because it's like the interrupt must be clear. It's like, okay, I feel hungry, I go to take my lunch. Because after lunch, your stomach is full already. But this signal must be clear. If you do not clear, then your brain, okay, always remember you are hungry. Then you spend hour to eat, then you will die, Chana. If they say you keep eating your lunch because your brain forget to clear this interrupt that which tell you are hungry, then you are in trouble, Chana. Yes or no? But we are people like this, John. Okay, he always believes that he's hungry. Then what's wrong? Because his brain forget to clear the signal sent by the stomach, which tells the brain that the stomach is empty. All right. So it's the same. Always remember to clear the interrupt. Otherwise, you'll keep doing the same thing. Right. Then that's it. Once you configure, then just run it. Run it means if you are the transmitter, write the data here. If you are a receiver, just receive data from here. Finish, right? And then monitor the internal signal. Internal signal may tell you data has been received, data has been transmitted out, all right? So whether the buffer is full or buffer is empty or something like that, you just follow the internal signal. And in case if you want to know whether there's a signal which has been masked out or not, okay, you can also check, all right? Also, you stop the signal to inform the CPU, but you still want to, you still have a possibility to verify whether signal appear or not, all right? So nothing has been lost, okay? So that's it. And you can also monitor the status of a buffer, all right? Because the data could be, size could be up to 16 bit. So this is why we provide, the hardware provide you a buffer. Buffer means additional super room, okay? Outside the hotel. That means give you extra A room to store the data only. This A room only store the data, okay? Not for other purpose. You just think in this way, give you extra A room there, all right? Okay, so then, okay, that's it. But when these rooms are fully full or half full or empty, so this hardware will automatically generate the interrupt signal. Here is a status is full, empty, etc. Okay, so you can read all this. Okay, so that's all for the lecture 2. We take a break of 4 minutes because we run out of time. Then we continue at 11:25. Okay.